In this problem, a person with his ear on the ground sees a huge stone strike the concrete pavement. Now he hears two different sounds, one from air and one from the concrete, and they are zero point 0.8 seconds apart. So now we need to figure out how far away did the impact occur. So if we know the time and if we know the velocity of sound in air and concrete, we can easily write distance equals velocity times velocity of sound wave in air times time it takes um, for sound to travel. And since two sound waves travel the same distance, that means the sound will travel faster in concrete and thus take shorter time. But yeah, they travel the same distance, but in concrete it will take a shorter time. And to check whether that's true or not, if you look at table 12.1, you'll see that in concrete the speed of sound is 3000 meters per second, and in air it's 343 meters per second. So clearly in concrete it will take much shorter time, right? But since it's traveling the same distance, so the velocity in air times time it should be equal to velocity in concrete times time in concrete. And so now we have a relation. So, and then we have this following this condition over here. And that simply says that time in air should be greater than time in concrete, and as they are separated by zero point 0.8 second, so we'll have T air minus T concrete as zero point 0.8 second. Now, following this equation, we can replace this T concrete by T air minus T second, because we see that if we take this guy on right side and take this guy on the left, we'll have T air plus, sorry, T air minus zero point 0.8 second, which is equal to T concrete. And that's what we're using there. And yeah, and then if we look at this equation and this one, we'll see that we can solve for T air from these two equations. So if we solve for T air, we'll end up having an expression like this. And so you should do the derivation and see if that matches or not. But yeah, and again, since we know that this is equal to our d, or the distance traveled, so we can easily replace this part over here and we get something like this expression, right? Now, the reason we want that is because we know we kind of know the velocities of air and concrete, of sound waves in air and concrete, but we don't know the exact time. So that's why we wanted to replace this time by some known values or known quantities. So now we have an expression where we only have the velocity in air and the velocity in concrete. So now if we go back to our previous board, we see that in concrete it's roughly 3000 meters per second, but in air it's exactly 343. Now we'll try to derive this velocity, or we'll try to get the accurate velocity of sound in concrete, or accurate speed of sound in concrete. And to do so, what we're going to do is we'll be using this equation. So this is equation 4, equation 11, so chapter 11, equation 14a, and it says that velocity of any material is equal to square root of the elastic modulus or the Young's modulus of that material divided by the density of that material. So for our case, since it's concrete, so I've taken all the subscript as concrete. So, and then we have to look at these two tables, table uh, 10.1 to get the density of concrete, and then table 9.1 to get the elastic modulus or Young's modulus of concrete. So we have the values from the table, and then if we put the numbers over here and solve for it, we get 2949 meters per second. And if we look at the initial number over here, we see that it's pretty close. So the exact value is 2949 meters per second. But yeah, we'll be using this exact value for our calculation. So again, this is the expression that we want. So now we know the velocity of concrete, and now we know the velocity. We always knew this one. So if we plug in all the numbers here, um, so this is the velocity of the concrete, and this is the velocity of air, velocity of sound in air, and we get something like this huge expression, and we'll have something like 310.5 meters, which is approximated as 310 meters. Thank you.